My name is Scott Linder. I'm a software developer at LLVM working on a compute compiler for GPUs. And today I want to talk about a new approach to debug metadata that we're calling heterogeneous debug metadata. So to give some context before I dive into that, I think it's illustrative to survey the kinds of challenges that we face with the current solution. And to make that more digestible, I've broken it down into three categories. First, multiple locations, which captures the inability to keep track of more than one location for a variable in the debug metadata, or rather more than one location at a single time. Second, dependencies and composites. So the design we have today makes factoring out expressions impossible, and it tends to interact poorly with a solution for multiple locations. And third, context. So the existing debug info relies on a lot of context, which often leads to confusion for compiler developers and also adds to the work the compiler has to do. And before we talk about the specifics of what's lacking in the current debug info, it might be helpful to kind of get a basic understanding and overview of what the actual debug metadata looks like today and how it works. So specifically, we're going to focus on the pieces that keep track of where source variables are during execution. And to do this, we have metadata nodes to keep an identity for those objects during compilation. So like di local variable is standing in for a function local variable. And because the location of these objects can vary from instruction to instruction when you're executing, we need to anchor that into the instruction stream through calls to intrinsics. So like LLVM dbg adder and LLVM dbg value. And we use arguments to those intrinsics to capture LLVM SSA value, that's the first argument. The source variable being described, so like the di local variable, that's the second argument. And something called a di expression, which I'll probably just refer to as expression for the rest of the talk. So that SSA value, it basically acts as an input to the expression, and when you evaluate the expression, you get the location of the variable. And this is probably as good a time as any to admit that I won't be going into great detail in many parts of the talk. For example, the particular ways that these two intrinsics differ would take a little bit too much to go into. It's not particularly important to us. And similarly, don't expect to be able to run any of the code verbatim. I tried to trim it down to make it easier to just see what's important. So with that out of the way, let's look at an example of how the current metadata would describe a single variable called var. So compiling this function with Clang or whatever front end, you'd get some that looks similar to this. Note that the di local variable and the call to LLVM dbg adder show up. So the first argument to LLVM dbg adder is an SSA value. In this case, it's var.alloca. The second argument ties it to the source variable, in this case, var. And the final argument, when evaluated with the first argument as its input, gives you a location for that variable. In this case, it's an empty expression, and there's kind of an implicit interpretation that gets used. But this seems hopefully straightforward enough. But what happens if the variable moves or it becomes unavailable at some point? Well, let's start with the same source program. But this time, let's say the compiler knows the variable's unavailable after some point in the function. So this is implemented by making these intrinsics overwrite or kill each other when you refer to the same source variable multiple times. So in this case, both intrinsics are referring to the same source variable var. The first one still refers to that SSA value for the alloca. And to say the variable's not available anymore, you can use undef. And effectively, this defines a range over which the variable is available in that location. The compiler could also use any other SSA value to effectively say that it's moved from one location to another. Okay, so we have some grasp on how debug info works in LLVM today. So let's look at the first challenge that arises, namely the inability to describe a variable as being in more than one place at the same time. But how can this happen? Well, one example is if the compiler caches a value from memory into a register, but it never writes that value back from the register to memory, and it continues to use the memory location. So concretely, let's say you have a loop that would normally repeatedly read from memory. So the compiler could promote that to a register for the duration of the loop, but maybe it still keeps that location in memory around for use after the loop. If it also proves that the value can't change during the loop, there's no reason for it to write the value back from the register into memory after it terminates. So in real terms, for the duration of that loop, it's in both locations. It's in memory and it's in the register. And if a debugger wants to update the value, the user has to write to it, it would need to update both, or it would be violating an invariant the compiler was relying on. But as we just saw, by construction, the current LLVM metadata doesn't let you represent that. If you define the new location, you're implicitly saying it's no longer in the previous location. So any change we propose needs to address representing multiple locations at the same time. And with multiple locations in the back of our mind, let's look at the next challenge, dependencies and composites. So today, when the location of a variable needs to be stitched together from more than one LLVM value, let's say a compiler has broken it up and treated each piece separately, but the same source variable is conceptually made up of some combination of the two. A pseudo operation gets added to the end of each expression for each of the pieces, which is effectively saying where it fits into the original source variable. So it's kind of an implicit expression of where it is, what its location in the final variable is. However, as each piece is now describing where it fits into that larger whole, there's no explicit way to operate on the whole. You effectively can't depend on more than one LLVM value to describe some part of the final variable. So to illustrate why that restriction is an issue, let's look at the same example from before. So our debug intrinsic is referring to that same source variable var and to the same alloca, and we're effectively describing the situation in the diagram in the bottom right, where the source variable and allocation overlap exactly. But what happens if the compiler decides to split up that allocation? Well, we need to update the expression for each piece to add that tag at the end saying, I'm actually only part of the original variable, and here's where I fit in. So like before, we tie both intrinsics to the same local variable. We update the expression for the first intrinsic to say we're actually just defining 16 bits of the source variable starting at bit 0. And then we can tie this to the allocation for that lower half. Then we do the same for the upper half, use the expression to say we're defining 16 more bits, but now starting at bit offset 16, and tying it to its allocation. So now the one-to-one correspondence is broken, and we have to conceptualize the final source variable in terms of more than one LLVM value, but the diagram's still pretty straightforward. One wrinkle that might stand out is the fact that we now have two intrinsics referring to the same source variable, but which are expected to be in effect at the same time. With the examples from before, you might expect one will end the other. In this case, the rules are essentially amended to support fragments so that non-overlapping fragments of a variable don't implicitly overwrite each other. So in those last couple of situations, LLVM fares pretty well in keeping track of the final source variable. But what if there's something computing a value over an entire LLVM value? So for example, let's say the final value is actually the value in the alloca shifted left by 1. Well, before we're describing the same source variable. To reflect the left shift, we can use an operation for the purpose, DWOP shift left. And the shift essentially applies to the value in the alloca used as the first argument, and we get the result we're after, where they're offset from each other. Note, however, that we did have to change the intrinsic we used from .adder to .value, and we had to add what's effectively a stateful kind of flag at the end, DWOP stack value. And again, I won't go into too many specifics about this, but keep in mind this is one of the examples when I talk about context dependency later. So putting these cases together, the final point of going into this example is that LLVM can't reasonably represent the combination of these two. And I'll apologize for an oversight. These should also include that same DWOP stack value from earlier. I noticed too late to add it back in. So in this case, we're talking about the same source variable var. We have the first allocation that we want to describe as being the first 16 bits of the variable. We have the second that we want to describe the second 16 bits of the source variable with. But if that case with the left shift occurs along with breaking up the underlying allocation, the fragment approach kind of breaks down. So to describe the value of the most significant bits, we actually need to depend on some of the bits from the lower half, in this case, just 1 bit. But that isn't representable with this fragment arrangement, at least not generally. So note that in this case, we could play with the fragment arguments to make the shift happen, but that's just for the specific case of a simple shift. If you have any other more complicated expression, it's impossible to just do the same thing each time and have valid debug info. And in most cases, including even these shift cases, LLVM currently just drops the debug info. So now also recall the issue of multiple locations in relation to this issue of dependencies and composites. So the same reality applies to each individual piece of a variable if we've broken it up. So without some way to effectively factor out and consider each piece separately, we're going to run into a combinatorial problem. So to illustrate that, let's look at another example based on the same one again, but this time let's add 2 nested loops. So at first, with no optimizations, we can say the variable is located at the composite of the 2 allocations. But things start to get a bit more complicated the moment any part of this variable is in more than one place at a time. So like the example for multiple locations from before, if we say that the compiler promotes the lower half to a register for the outer loop, but it still retains the in-memory copy and it doesn't write the register back after the loop terminates, then we need some way to represent that it's in multiple locations. But because we have no way to describe just that piece, no way to factor it out, we have to essentially describe that inline in the original source variable, the description for it. So we end up with at least 2 expressions, one saying this is always located in the composite of the 2 allocations, and another saying that for the duration of the loop, the outer loop, it's also located in the composite of this SSA value and an allocation. So okay, in this case, we have more expressions to maintain, but conceptually, it is in 2 places, so we need at least 2 expressions to represent where it is. So we can't do much better. But what if the high allocation is also in multiple locations? Let's say, in this case, it overlaps partially. It's in the inner loop. It's in multiple locations. So now we're on the hook to describe every combination of locations among these 4 distinct LLVM values. And hopefully you can see adding more is not the kind of linear solution that we're looking for in representation. And it also leads to more verbose debug output. The debugger has to chew through all of these redundant locations. In this case, you'll see var.alloca.low appears multiple times in the final location for the same instruction. So if it updates this variable, it will repeatedly write to that same location. Finally, a challenge that's cropped up in small ways so far is the dependence on context. So today, before you even start to interpret any part of an expression, you need to know what intrinsic is referring to that expression. You need to know the kinds of values you're using as input to the expression, and you have to consider the whole expression, including those pseudo flags at the end, like fragment or stack value. And even if this is to sound from a technical perspective and it models everything, the real issue is that the design doesn't compose once more than one input or dependent expression is involved. It creates more work for the compiler than the more context-free approach that we'll describe. But surely we can just incrementally nudge the current solution into this better direction, right? Here I don't think it's quite that simple, because at each step of the way, the changes need to be well-defined for multiple intrinsics. I've shown 2, there's at least one more that's kind of soft deprecated currently. And because of the design of the programmatic interface to the expressions, the updates also require potentially a lot of changes at many call sites for each change. And this movement towards this kind of incremental approach, there's been some movement there, like a recent addition called DI list. But currently, all of these have been for specific use cases, and generalizing them, it doesn't actually address these context issues and all the 3 challenges that we've talked about so far in a holistic way. So it runs into some of the same problems eventually. So to finally get back to the original focus of the talk, our new approach, which we call Heterogeneous Debug Info, tackles all of the challenges that we've described so far. And don't let the name fool you. It's a reflection of why we're interested in the topic, being a company working on GPUs, but not a restriction on the applicability of it. So this approach is generally applicable to traditional CPU architectures alone, and it's designed to replace the parts of the existing debug info rather than supplement or be an addition for just GPUs. So it supports symbolic dependencies between source variables and a new type of metadata node that we call a DI fragment. So a DI fragment behaves basically just like a DI variable for most operations, most transformations. So there's a new abstract-based class called a DI object to just capture the idea of some object that you can describe the location of. Our approach also supports multiple concurrent locations by introducing a new metadata node we call DI lifetime. There can be many DI lifetimes all referring to the same DI object, and each of them represents just one location for that object, but there's not the implicit ending of one lifetime when another is introduced. And the combination of these elements means the expressions for variables, like in the left shift case from earlier, are always complete. So they can operate over composites or any complex expression without any special treatment. Or put another way, the approach facilitates mechanical updates the compiler can always do and that are always correct. So let's look at a simple example. This time we're going back to just a single variable in a single location. So we still have a DI local variable from before, but now it's referred to by a DI lifetime, not an intrinsic directly. So this is representing a single location for this local variable. The DI lifetime is bounded or anchored into the instruction stream by calls to these new intrinsics, LLVM.dbg.def and LLVM.dbg.kill. And the second argument to the def intrinsic defines what we call the referrer of that lifetime that it's referring to, which essentially is the explicit input. So you'll note that there's no implicit input to the DI expr. I'll just call it expression from now on. Whereas in the previous case, there was an empty expression and that had implicit meaning in terms of how to interpret the input and the direction of the input. Now all of that's always explicit in the expression. So there's an explicit DI op refer to bring in that refer from the intrinsic, and there's an explicit dereference because we're actually looking at the contents of the alloca rather than the pointer represented by it. So separating the lifetime concept from the objects themselves means we can describe multiple locations at the same time. So as before, we have the single DI local variable, but now we have multiple DI lifetimes. We still have that first DI lifetime bang 1 from before, defined over some range in the function with the intrinsics. But now we also have a DI lifetime bang 2, which overlaps partially with the former in this case, and where the two lifetimes overlap, the object naturally is in multiple locations. We can describe the fragment case as well. So starting with the simple example again, let's follow the mechanical updates the compiler would make to reflect this. So we're talking about the same local variables before. We have made two new LLVM values by breaking up the 1. So we create two new DI fragments. This happens regardless of the complexity of the existing expression for the variable or the type of object we're describing, and works on any inputs. And in fact, this is agnostic to whether we're optimizing a source variable directly or the fragments generated by some other optimization that came before us. The same mechanical approach always applies. And because each fragment is an object in and of itself, just like a variable, we can describe the locations for each using the lifetimes. So we'll make a lifetime for our first fragment, define it using an intrinsic, repeat for the second fragment, giving it its own lifetime, defining it with another intrinsic. And finally, we'll just replace the DI op refer in the old expression for the local variable with a composite operation, describing exactly what we did, which is when we broke it up to get the original back, you just put them back together. And in this case, we need to add something to conceptually represent that we want the address of that final object, even though it may not exist now. Before we had an alloca, now really it's two things put together. There's no address for both together, other than conceptually. So we'll add DI op adder. And we just replace the refer operation with this and don't have to look at the rest of the expression at all. In this case, the rest of the expression is just DI op deref, but we didn't even need to consider it. And to actually depend on those fragments that we made, we can just use them as object arguments to the lifetime and then refer to those in the expression using diop-arg. So again, there's no implicit inputs anywhere. And this is the factoring that makes multiple locations feasible. So the fragments independently can have multiple locations without the combinatorial problem of the current representation. And finally, another thing this kind of mechanical context-free interpretation gives us is having a pass-agnostic way to kind of canonicalize or clean up expressions. So there's no diop, deref, or diop adder in this one, and that's because the general rule can be applied that the two cancel each other out, and this doesn't need to be done in each pass. And then really quickly, just from before, the same issue of not being able to look at the rest of the expression, or needing to look at the rest of the expression. When the shift left is there from before, you can just not consider it. All the same mechanical approaches apply. It's at the end, and semantically, it represents what we wanted originally. And really quickly, so the reason we call it heterogeneous compute is AMD GPUs have many address spaces, so the implicit indirection that's in expressions becomes a problem. This doesn't expose that, it doesn't have that implicit problem. And the dependencies and composites come up a lot more because we have very large vector registers that we use pieces of for many purposes. And that is the talk. Thank you.
Thanks, Scott. We're a little tight on time, but there are a couple of mics. I can always bring one around if anyone has questions. One down here.
Perfect. Thanks for your talk. So as far as I understand, you're really trying to kind of replace the existing debug metadata intrinsic with a new system that you say is better. And I believe that because I don't know any better. But there's also a different approach, like there's currently a proposal to replace the existing system with something that is, the same but attached differently, like attach it to instructions rather than attach it to intrinsic. Should we try to, rewrite it once instead of rewriting it twice, just one after another?
Yeah, definitely. I think the approach you're talking about, we've looked at cursorily, but we believe it's kind of orthogonal in a sense that maybe we don't use intrinsics to define the lifetimes in this way, but the same fundamental idea, we need a new node to represent the idea of the location of something, whether we define it by attachments to instructions or calls to intrinsics, should apply in either case. So definitely it would be a lot less work if we could align doing both at the same time, do them once, and it would not be such a tumultuous transition multiple times. But
other questions? All right, since we're already a little pressed on time, we'll wrap it up here, and thanks, Scott. And there's a tea break in the hall.